then I'm going to pick up right where we left off. We were talking about hashing, and the idea behind hashing is to move beyond just indirect addressing and simple addition to leveraging the power of more math to do useful things, right? And so the idea that we've been exploring is the idea of doing hashing as a kind of random placement for load balance. Right, where we want to fit a collection of n items into space S. And if we just put all of the items in at random, then we would have sort of an average n over S items per bucket. And in particular, if S is bigger than n, this gives us an average of a constant number of items per bucket. And that gives us an average of constant lookup time for items in this hash table, right? Now, we talked last time about the drawbacks of doing truly random placement. Namely, if you place things randomly, you don't know where you put them, and so you can't find them, right? So we introduced this idea of pseudorandom placement. Okay. And we introduced this idea of pairwise independent hashing. Where we take a key x, where we pick a random, let me just make sure my notation matches. Yes, we pick a random A and B modulo some prime P. And we then hash any x in the range from 1 to p into the value ax plus b mod p, right? And we proved last time that h of x and h of y are uniform and pairwise independent if x is not equal to y mod p, right? And pairwise independence, which I defined last time, was all that we needed in order for our basic analysis to work, right? So the expected number of collisions with item I, right, was equal to the expected value of the sum over j of Cij, right? But because the positions, sorry, I should be using x and y again. Let's stick with I and j. Because the positions of I and j are pairwise independent, right? This is the sum over j of the probability that I collides with j. But since since these values are pairwise independent, each of these was just equal to 1 over p, right? And so that entire sum was n over p. Yes? And so that worked out. That works out very nicely. Again, as long as p is larger than the number of items n that you're storing, you end up with a constant number of collisions in expectation, which means you get constant lookups in expectation. So that was just review of what we did last time. There was this little detail, which I can't remember if I asked you to look at it or not. What if you have some non-prime hash table size that you would like to use? Okay. How can you sort of preserve the benefits of this hashing approach, right? If you start going mod S, it's not a field anymore. And so it's harder to prove things. Yeah?
We can choose our hash function to be first mod P and then mod S afterwards.
Exactly.
And we choose P to be considerably larger than S. And then it so it approximately works. That was the argument you gave.
Yes, exactly. Right? So what we do is we do the thing that we already did, right? We pick a P that is much larger than our hash table size, right? And so we've already made the argument that inside the parentheses we have uniform pairwise independent items. So everything is nicely spread out, right? We then take it mod S, but if we think about that, we're basically taking the range from 1 to P, and we're just wrapping it around a circle of size S, right? And so essentially, the items are uniformly pairwise independently distributed on the spiral, which means the number of them that lands at any particular angle is still going to be approximately pairwise independent and approximately uniform, right? There's going to be a slight difference because some parts of the spiral have one extra winding compared to other parts of the spiral. And that's necessary, right? I mean, can we pick P so that it's, can we pick S or P so that it's exact and we don't have to approximate? Yeah?
And P is prime.
P is prime, so S can't divide P, so there's going to be some remainder somewhere, and that's going to leave a little bit of, that's going to make a little bit of mess, but not enough to matter, okay? And so this works great, it's implemented everywhere, very simple, very fast, very practical, really everything that you want. Except not quite, because we're theoreticians and we always want more. So let's talk about what more we could hope for. Boy, these chemists press hard with the chalk. Ugh. Okay, so we've already managed to achieve constant time lookups in expectation. What could possibly be better than that? Yeah?
Even in the worst case constant time lookups?
Yeah, how about worst case constant time lookups? Right? Let's do away with that expectation. In fact, let's aim for no collisions. So we're now going to study perfect hashing. Where the goal is to hash n items with 0 collisions. Okay? And having 0 collisions is, that's way better than having order 1 in expectation. Right? With 0 collisions, you don't even, you're not going to have to use linked lists to store the items, right? You can just pop them into the array because nothing else is going to land in the same spot, right? The lookup time is one memory access, not order 1 memory accesses, right? So can we do this? Well, let's assume we have a fixed set of n items, and we want to build a perfect hash table or a perfect hash function for it. Right? Now, here, it seems like we're asking for a lot because like even a random hash function is going to have collisions, most likely, right? So we're asking to be even better than random, okay? And if we immediately tried to hash those n items to n space, we would face some challenges. But let's try using more space. Okay. So the question is, what size s bigger than n is sufficient for no collisions of a random hash function? Okay, so I'm going to pick some s which is larger than n. I'm going to hash all of the items. I'm going to hash my n items to that larger space s. How small can s be if I still want to have a decent chance of getting no collisions at all?
Square.
What was that?
Square.
Square. Right? The answer is, well, let's derive it, or let's figure it out. Let's just ask, what is the expected number of collisions that we get from this random hash function? Okay? Now we're talking about collisions among all pairs, right? Before, we were analyzing the number of collisions with item I. Now we're just looking at the number of collisions between all pairs of items, right? So that is going to be equal to the expected value of the sum of these indicator variables, right? And how do we evaluate that? Yes?
Linearity expectation?
Absolutely, right? Sum over ij of expected value of Cij. Now what? Yes.
By pairwise independence, each individual event for the probability of one over S.
Exactly, right? Each of these expectations, right? It's an expectation of an indicator variable, which means it's the probability. The probability of the event is the probability that the two items collide. And because we're using a random hash function, or as we've seen, even if we're just using a pairwise independent hash function, this probability is 1 over s. And so now how do we finish? Yeah.
So you expect less than one collision, right? Because the number of pairs is less than n squared.
Exactly. The number of pairs is n choose 2, right? And so this is roughly n squared over 2s, right? Or I should say it's less than n squared over 2s, right? So in particular, this is less than a half if, for example, s is equal to n squared. And so this derives the answer that was given to me, okay? As long as the space is quadratic in the number of items that you're hashing, you can hash and get no collisions at all. Or sorry, get at most half a collision in expectation. But half a collision is not no collisions, right? Half a collision is half a collision. So how can we get from there to what we want, which is no collisions? Right? Well, so let's think about this, right? I'm hashing these items, and what I've just derived is that I will expect half a collision. Will I ever get exactly half a collision? Can I get half a collision? No, that doesn't even mean anything, right? What can I say about the number of collisions? Well, it's going to be an integer, right? So I can't get half a collision, but how can I argue about getting zero collisions? Well, this is where we pull out sort of a third key randomized algorithms trick, which is Markov's inequality. Okay, which was the theme of Lake Wobegon. The Prairie Home Companion was a radio show many years ago where they said it's coming to you from Lake Wobegon, where all the women are strong, all the men are good looking, and all the children are above average. So that's problematic, right? And Markov inequality kind of points at the problem. It says that the probability that a random variable x is bigger than some quantity t is at most the expectation of that random variable divided by the quantity t. Okay? And what that's basically a generalization of, well, if everything was above average, then the average would be above average, right? Which can't happen. So whatever the average is, some things have to be above it and some things have to be below it. And if even a little bit of stuff is way above average, that's going to drag the average up, right? So we use Markov's inequality just about everywhere. We also use it to derive stronger bounds like Chebyshev and the Chernoff bound, which we probably won't be using in this class. But this is good enough for us because in our case, we're going to use the total number of collisions as our random variable. And so now we can say that the probability that we have greater than or equal to one collision, right, is at most what? Is at most 1/2, right? It's this quantity n squared over 2s. Right? Because the expectation is 1/2 and the t that we're looking at is 1. Okay? So again, this is a technique that we use all the time to transition from a small expectation to a decent probability of getting a small value. Right? So in particular, in this case, we're using the integrality of our number to say, well, the expectation is less than 1, and that gives us a decent chance of getting a value 0. Okay? All right, so now we've gone beyond, a random hash function gives half a collision in expectation. Now we can say a random hash function gives us no collisions with probability 1/2. So that's nice, but there still is a chance that we might get a collision. So if we try a random hash function and we get a collision, what should we do? Try again, right? So this is the next big idea in randomized algorithms. It gets a fancy name, amplification, right? If at first you don't succeed, just try again. Okay. So generate a random hash function. If it works, great. If it doesn't work, try again, right? The probability that you need k attempts in order to get no collisions is the probability that k minus 1 of your attempts fail. So it's at most 1/2. Actually, the probability you need exactly k attempts is the probability that k minus 1 attempts fail and the last one succeeds. So it's basically 1/2 to the k power. Okay? And what is the expected number of tries that you need to do in order to get one of these collision-free hash functions? Yeah? What's that? 2, right? 1 over the success probability, which is equal to 2, or at most 2. Okay? So this is pretty much all the probability that you need to know for this class, because this is not randomized algorithms. You should take that next year. It's almost all the probability that you need to know for randomized algorithms, but there's a little bit. It was just random. Okay, so we can get a perfect hash function if we're willing to use a lot of space. Could we get by with less space? What if we tried hashing to smaller? Is it possible that with a smaller space, we have still a decent chance of getting no collisions? So, it looks to me like there are roughly 23 of you in this room, right? So if I hashed you all to your birthdays, would there be a decent chance of having no collisions? Yeah, that's kind of where the 1/2 is. But if there's a little bit more of you than 23, right? What happens to the chances of a collision? It goes up very quickly. Okay? So there's this problem called the birthday paradox. Which says that if S is less than n squared, collisions become likely. Okay. The probability that you manage to avoid a collision, you can basically write out sort of as you do the hashes one at a time. You get this product, which is approximately e to the minus n squared over 2s. So here's that same quantity again, right, from the expectation, right? And as n squared grows beyond 2s, you get this exponential decay in the chances of avoiding a collision. Okay, so you're out of luck. So n squared is kind of the best that we can hope for in space with this sort of naive approach of just growing the available space. Okay. Everybody knew this right away. This is pretty obvious, but Fredman, Homlosh, and Zemretti had a really cool insight that made this better. Okay, I'm not really sure how they thought about this. This is the same Fredman who developed Fibonacci heaps. It's all this sort of little mafia of data structures people. Of doing what they call two-level hashing. What you do is you hash your n items to n buckets. Okay. Then you put each bucket in a quadratic hash table. Okay? Tiny little change. Right? Instead of just going directly to the destination, you have a hash table that points to hash tables. Okay? And this turns out to work great. Okay? Assuming we do this, right? Actually, I should say we perfect hash. So, right, you're going to keep building these quadratic size hash tables without collisions until you get one that doesn't have collisions for each bucket. So how long are lookups going to take in this data structure? Yeah? Still constant, right? Now it's 2 steps instead of 1. You take the item, you hash it to the first level of the array, and then you hash it to then you look in the appropriate hash table for that bucket. Right? So this is constant time lookups. worst case. So really the only question is, well, what is the only question? Space. How much space does this take? Well, it's n at the top level plus the sum over all of the, whoops, where'd we go? Sum over all of the buckets of the size of that bucket squared, where this is the number of items in bucket B. Right? So all we need to do is figure out that size. Now, actually, we're going to be looking at that size in expectation. Right? Because these buckets are populated at random. So the sizes of all of these buckets are random. So what can we say about this expected size? Well, I'm going to ignore the n. How can we measure the square of the size of a bucket? Well, I'm going to write that in a funny way. I'm going to denote the size of the bucket as sum over b. And now I'm going to take a sum over all items I in that bucket, or sorry, sum over I of the indicator that I is in that bucket. Okay, and then I'm going to square that. Right? I'm just going to be summing up the indicators for which items are in bucket B. Make sense? Okay, now how do I evaluate that? Well, here I have the square of a sum, right? So how do I expand that? Well, I expand it as a sum of squares, right? Right? And here I and j both range over all of the items, right? So I can write this. There's going to be pairs where I and j are equal, right? And then there's going to be all the terms where I is not equal to j. Let's just call this, let's just do I not equal to j of I is in B and j is in B. Yes? So now let's simplify. So this indicator variable squared, how can I simplify that? Yeah? Yeah, squaring an indicator variable doesn't change it because it's 0 or 1. Right? So what is this quantity? The sum of the indicators for I being in bucket B. Yeah? Size of B, right? Now, what about this one? So here we have an indicator variable for I and B and j and B. By itself, we can't do anything yet. But notice that we're now summing this over all B, right? So should have written a little bit smaller, but let's go over here. So now what we have is a sum over B of the, or an expectation is out here, S sub B plus this sum of I and j both being in B, right? But now we're summing this over all B. So what is the sum over all B of S sub B? It's n, right? And now, what's this quantity? The sum over all buckets of the sum over all pairs of items I and j of having I and j both in bucket B. What is that measuring or indicating? Yeah? Exactly. So if I look at the joint indicator of I and j both being in bucket B, and I now sum it over all the buckets, what that's telling me is that I and j have collided in some bucket. Right? This is the indicator that I and j have collided inside of bucket B, and now I sum it over all buckets B. So this quantity is just the sum of allCij's. Yeah? Yes, thank you. Okay, because there's an ij and also a ji in that sum. Okay. Actually, no, it depends on how I define my collision indicator. Right. Okay, and what can we say about the, so we have an expected value of n, that's certainly just n, plus and what is the sum of Cij's in expectation? Remember, this is now measuring at the top level of the hash table, right? What we're doing here is we're hashing n items to n space. So what's the expected number of collisions? Have I lost everybody, or were there just some really big parties last night? It's order n, right? Because again, we have n squared of these terms, and each of them is a collision with probability 1 over n, right? So n squared times 1 over n, which is order n. So the expected total number of collisions, and again, with plain old 2 universal hashing, we were just looking at the number of collisions with one item. But now we're looking at the expected total number of collisions when you hash n items to n space, and that number of collisions is order n. Okay? But bizarrely enough, that total number of collisions also turns out to be the expected size of the sum of squares of bucket sizes. And that is the space that's used in the second level of the perfect hash function. So what we've just shown is that the second level space is order n. And so this simple trick, I don't know how to come up with it, but this simple trick of just hashing to 2 layers gives you order n space and no collisions. Yes?
Sorry, I'm still a little confused as to how this gives constant time lookups in the worst case. Because, like, if you're hashing n items to n buckets, like, you can never guarantee that there aren't any collisions.
Oh, no, what we've shown here is that there are collisions, right? The expected number of collisions is n. Right? But that's just at the top level, right? So at the top level, we will have buckets with more than one item in them. And we take each of those buckets, and we build a hash table for the items in that bucket. That second level hash table, its size is the square of the number of items in the bucket, and therefore it's a perfect hash table. I mean, we keep regenerating it until we get no collisions.
Oh, okay. Wait, so you regenerate every single, like, so expected time it takes to generate such a table might not be.
Good. So what I'm talking about right now is the creation of this table and how fast the lookups will be once you've got it.
Okay.
Okay. And so does everybody buy that this defines a data structure that you can construct, which will give you constant time, worst case constant time lookups, and use only order n space? Yes.
So I think I might have missed some features of the specification of this problem. We're assuming that we already know all of the items that we want to put in the hash.
Good. So that's where I want to go next, right? What we've now shown is that if you have n items, you can execute this procedure and create a hash table, a perfect hash table for those n items. Right? Now let's ask about the construction time. How long will it take me to build a perfect hash table for those n items? What do I need to do?
Count the time you need to, how many times you need to reconstruct the table.
Or well, how many times do you need to try to construct the table, right? So this is a randomized construction, and we're talking about expectations, right? What I told you was that the expected number of collisions at the top level was order n, and therefore that the expected amount of space that you would need to do a quadratic table at the second level is order n. Right? But that's an expectation, right? So what do? Well, we try doing a top-level hash, and we look at what that does to the distribution of the items, and what is the sum of squares of bucket sizes. Okay? And if the sum of squares of bucket sizes is order n, then we're happy and we can proceed. Right? What if the sum of squares of bucket sizes is not order n?
How do we even define order n in this case? 'Cause, I mean, once we're working on it, it's constant, right? The number of
Well, sorry, I don't want to figure out exactly what the constant is. I think it can be, 2n. It can be 2n or 4n or something like that, right? So if it is smaller than that, we're happy. If it's larger than that, what should we do? Try again, right? Just keep trying until we get a distribution of items where the sum of squared bucket sizes is linear. Okay? Now, in order to do that, we need to say that we have a again, we have to move from an expectation to a probability, right? I said that the expected size of the sum of squares is linear. How do I know that I have a decent chance of the sum of squares being linear? So I don't have to try this too many times. Yeah, it's the Markov inequality again, right? The expected size is order n, and so the probability that you're more than twice that is only a half. So with probability a half, you're within 2 of your expectation, and so your size is linear. Okay? And so just like the analysis that we already did here, right, you just keep trying until you succeed. There's an exponential decay in the chances of your failing over many iterations. The expected number of tries is 2. And so you get a top-level hash function that has the right distribution of bucket sizes. Once you have all of the appropriate bucket sizes, now we're back in the world of building a quadratic size perfect hash table, which we've already discussed, right? You try hashing to a quadratic space, and if it works, you're done, and if it doesn't work, you try again. Right? And with all of this, you're using these 2 universal hash functions that we talked about to do the distribution of items. Okay? So all of this means that you use this amplification technique, right? You keep randomizing the top level until you succeed, right? And this is going to take order n time in expectation. right? Because each try is going to, it's going to take you linear time to spread out the items and count up the squares of the bucket sizes, right? So it takes you order n time to find a good top-level hash function. And then you randomize each bucket until you succeed. And this, again, is going to take you order n time. And so in expectation. And so given your set of n items, the expected time to construct a perfect hash table for it is linear. And once you have done so, the lookup time is constant, worst case constant. Everybody happy with that? OK. That's pretty much all I want to say about perfect hashing here. I'll mention that in terms of the constants, okay, if you just sort of work through everything as I've described it here, it turns out that you use about 13n space. Okay? The number of machine words, assuming each key can fit in a machine word, the number of machine words is about 13 times that. It's pretty easy to get that down to 6n space. The authors actually managed to get it down to n plus little o of n space. But this required them to be very creative and hacky. Essentially, what they do is they use the fact that when you build your random top-level hash table, right, probability tells you that some of the cells are going to be empty, right? It's not perfectly, you don't perfectly distribute the n items over the n space. Instead, you're going to get extras in some places and holes in other places. And so you actually use the empty cells of the top-level table to store the items. And you use this little order n extra space to kind of say where you're putting the particular items for each associated with each bucket. So it's pretty complex, but it can be done. And so now we're really optimal, right? We're using not order n space, but n plus little o of n space. And we're still giving you constant time worst case lookups. Okay. Now, another thing that you might like to have is what's called dynamic perfect hashing. Right? One of the things that we like about hash tables, so there are a lot of applications of hash tables where the set of keys is fixed, and you just need to do a lot of lookups. And for that, building the hash table in advance is fine. But sometimes you need to be able to insert and delete items as you go. And it turns out that you can, right? What you do is you sort of track the perfection of your hash table during inserts and deletes. And you sort of fix your table when it breaks. So you've got this two-level hash function, and you use it until some items collide. And when those items collide, you rebuild the part of the hash table where there's a problem. Right? And if you do this cleverly, you can still manage order 1 amortized inserts and deletes in expectation. And you can still manage order 1 worst case lookups. Okay? And if you work even harder, if I am recalling correctly, you can even get rid of the amortization here and really achieve worst case constant time for everything using the ideas from perfect hashing. Okay. Yes?
What are success criterion in the top level? So we allow collisions in the top level?
We do allow collisions in the top level. And what did we require in order to get a good perfect hash function was that the sum of the squares of the bucket sizes be linear, because the sum of the squares of the bucket sizes is what determines the total space of the second level. And so that's the success criterion for the top level, is that the sum of squares be linear. Any other questions? All right, so this brings us to the end of the data structures portion of the class. Now we are, yes, thank God we're done with all of those logs. Now we're going to be moving into combinatorial optimization. We're going to be spending some time talking about max flow and min cost flow and linear programming. We'll pick that up after we take a 2-minute break to let everybody sort of wash all those silly data structures out of their head.
Curious, do you know what the optimal little o of n term is?
No. I think it's like n to the 2/3 or something, but I really don't remember. If you can't find it, you can email me and I can dig it up. I know it's in the Fredman Comotion Zemmoretti paper that where I wrote down the author. Where did I put those authors? Yeah, Fredman Comotion Zemmoretti. Okay. I think it's 2/3, but you just go look at the paper.
I'm still confused about the two-level hashing thing.
Mm-hmm.
So, for example, there's a top level and there's another level, right?
Mhm.
Second level.
Mhm.
So, for example, when a number comes in,
Mhm.
first hash it into a top level bucket.
Right, and the top level has pointers to the second level hash tables. Each entry in the top level hash table is a pointer to another hash table.
Each entry in the hash table is a pointer to another hash table. Oh. So what's the point of the bucket size? Why?
That tells you how big the second level hash table has to be.
So we're constantly updating the size of the second level.
Well, again, this whole construction is predicated on having your n items to start with and building the hash table for those ones. If you insert and delete items, then everything's going to change, and you're going to have to that's the dynamic perfect hashing that I talked about at the end.
So for the construction, for the offline algorithm,
Mhm.
so you got a lot of numbers, and you can see like how. So you are constantly reconstructing the top level to.
No, because again, you've got the numbers to start with, so you just build one top level that works. And in order to work, you need the sum of squares of the bucket sizes to be small.
So how do you define work for the top level?
That the sum of the squares of the bucket sizes is linear.
It's kind of linear. Okay. So it is. All right. So we first see like how many numbers are in each like top level bucket,
And then we take them and put.
construct the second level thing. Okay. So what's the point of randomizing the second level?
That's how you get a perfect hash function at the second level.
That's how you don't get collision.
Mhm.
Yeah. So you don't expect to reconstruct the second level many times, right?
No, again, the set of items is fixed, so you just build it once. You find a second level function that has no collisions, and you just use that.
But the process of finding this working second level requires randomization, right?
Yes. That's where we use this random hashing into quadratic space.
Yes, thank you.
Sure. All right, let's resume. So I got some questions during break, which I'd much rather get during class, because then everybody else can get the answers as well. And so I'm going to sort of make this more concrete. To do this two-level hashing, we create a top-level hash table, and we hash all of the items to different buckets in the top level hash table. Okay. And then and that is a 2 universal random hash function. All right? And each of these buckets is going to have a certain number of items in it. Right? We then build for each of the buckets a quadratic size second level hash table. Right? To hold the items that landed in the bucket of the top level hash table. And so the top level hash table is just going to contain pointers to these second level hash tables. And by our analysis of hashing to quadratic space, we can arrange for these second level hash tables to have no collisions among the items that were stored into the second level hash tables. So when you want to do a lookup, you go to the top level, you hash to an entry in the top level. That gives you a pointer to a second level hash table. Then you hash in that second level hash table in order to find the item where it will have no collisions because of how you built the second level hash table. Okay, so hopefully that removes any confusion about how this data structure is built. Okay. Okay, so we're now going to be starting to look at combinatorial optimization. And combinatorial optimization is about this collection of problems where you're trying to optimize over sort of sets of things. So a lot of combinatorial optimization problems, the ones we're going to be looking at first, are over graphs, and you're trying to find various optimal subsets of edges. So the shortest paths problem, which you've already seen, is a combinatorial optimization problem, right? It's to find the set of edges that form the optimum path on from a given source to a given sink, right? And so, yes, there certainly are numbers involved to give you the value of the path, but what you're looking for is there's a set structure, and that's what makes it combinatorial. And we're going to be looking at several combinatorial optimization problems, and we're going to attack them all the same way. First, we're going to want to understand what makes a particular solution feasible. Which solutions are allowed to the combinatorial optimization problem? And can you quickly understand, and can the computer quickly check whether a particular proposed solution is a feasible solution to the problem? The next thing that we're going to try to understand, before we talk about actually finding the optimum solution, it's very useful to talk about verifying the optimality of the solution. So if somebody gives you what they claim is the optimum solution, can you check whether it is? Okay. This ought to be, at least intuitively, easier than actually finding the optimum solution, right? The next thing we're going to ask about is whether it is always possible to find a way to improve a non-optimal solution. Okay, many of our solution techniques will involve starting with a non-optimal solution, checking if it's optimal, and if it's not optimal, make it better. And just keep doing that until you're able to verify that it is optimal, right? Roughly speaking, if you can do both of these things, then you have an optimization algorithm, right? It may not be the best optimization algorithm, but it will be an optimization algorithm. But only after we've done those things will we investigate how to actually find the optimum solution. All right, so the first combinatorial optimization problem that we're going to look at is the maximum flow problem. And we have to look at this problem because it is the most important combinatorial optimization problem. It's always a little bit sticky because half of you have seen it before and half of you haven't. And so I apologize to those of you who've seen it before because you're going to be bored for a little while. And I apologize to those of you who haven't seen it before because I'm going to go fast because half of you have seen it before. So I'm going to sort of take an average pathway, and we'll quickly end up at things that none of you know, so it'll be a fair playing field again. So in the maximum flow problem, we're given a graph G, and it can be directed or undirected. The edges will have capacities which we denote by U, or by specifying their endpoints. And a couple weeks from now, you'll understand why we couldn't use C for capacity. Okay? But it has been U ever since the start of combinatorial optimization, and so we're going to stick with that. And while you can talk about max flow in undirected graphs, it's less ambiguous or less confusing if you focus on directed graphs, and that's what we're going to do. You also have a source vertex S and a sink vertex T. And your goal is to create a flow, or an ST flow. Which assigns some value f of E to each edge E, such that the flow is conserved, which is to say that the sum over, for any vertex V, the sum over neighbors W of the flow from V to W minus the flow from W to V is equal to 0 unless V is the source or the sink. Okay? So notice this is summing over all of your neighbors. This is not saying that on each edge the flow has to cancel out, but it's saying that the net flow, right? The sum of f of VW is the flow on all of the edges leaving V, and that has to equal the flow on all of the edges entering V. Okay. The second requirement is a capacity constraint, that the flow on any edge VW is at most the capacity of that edge VW. Okay. And what you want to do is maximize the value of this flow, which is defined as the sum over all of the neighbors of the source of the flow leaving the source minus the flow entering the source. So it is just the net flow leaving the source vertex. Okay, now you might ask, why did I pick the source vertex? What about the sink vertex? Well, one of the things we'll prove pretty soon is that the net flow entering the sink vertex has to equal the net flow exiting the source vertex. So we're not actually making a choice between them. Yes? Oh, I'm sorry, that's an F. Okay. So that's the definition of a flow, and of the max flow problem, rather. The definition of a flow is that it is of a feasible flow is that it is any set of flow values that satisfies the conservation and capacity constraints. And the maximum flow problem is to find a feasible flow that satisfies these constraints and that has the maximum flow value leaving the source. Okay. Now, there is an alternative specification of flows where you talk about net flow instead of absolute flow. So in this formulation, oh, actually, sorry, there should be another, besides, we also ask for the capacity, for the flows to be at least, to be non-negative in this definition, okay? So this is sort of an absolute flow where you can have some flow going from V to W and some flow going from W to V. In a sense, that flow is just going in a circle and isn't accomplishing anything. So you can talk about a net flow formulation instead, where you have this skew symmetry where FVW denotes the net flow going from V to W, and that's always just equal to the negative of the flow going from W to V, right? And now your conservation criterion, since you've already reduced to the net flow on every pair of edges, is just that for NEV, the sum of flows of net flows from V to W is equal to 0, unless V is S or T. And now the capacity constraint is just requiring that the net flow be less than or equal to the capacity. You'll notice that in one of the two directions, if the flow is not 0, then in one of the two directions it will be negative, and so this will be sort of trivially satisfied, assuming the capacities are positive. But in the other direction, this capacity constraint will actually apply, right? And now the value of the flow is just the sum of the net flow from S to V. And if you like to think in terms of matrices in linear algebra, this is kind of the natural way to talk about flows. But if you like to think in terms of physical quantities, I think this tends to be more natural. And I'll try to remember to tell you which one I'm using. But it should be pretty clear from context. So to start our understanding of flows, let's try to understand a little bit about how they can be decomposed into simpler things that we can understand. So again, sort of the physical intuitions for flow are pretty obvious, right? You've got a big network of pipes, and you've got a source of water or something in one place, and it's going to go flowing through those pipes and come out at a sink somewhere else in the network. Okay? And the flow is measuring the amount of water flowing per unit time through each of the pipes in the network. Now, what might be the sort of structurally simplest example of a flow? Yes? So zero flow is certainly very simple. Yes, and I will definitely take that one. And as long as the capacities are non-negative, it's going to be a feasible flow, right? And we're going to use that later on. What's a simple example of a non-zero flow, of a flow that has value? What's that? A chain, or the term we usually use is a path, right? So you just find a path from the source to the sink, and you send flow along that path. Okay? Now, in general, flows can be much more complicated, sort of branching out in different places and coming back together in other places. But it turns out that they're just paths in disguise. So the first very important theorem about flows is that any flow can be decomposed as a sum of flow paths and some other stuff, which we will discover as we work through the proof. Okay? So even though it may not look like it at first glance, any flow is just a bunch of paths of flow running from the source to the sink. Question?
Strictly speaking, just flow that doesn't branch.
It doesn't branch. It doesn't separate. It doesn't come back together. It's just like it's a path. It's just one chain of edges going from the source to the sink.
Is it allowed to intersect itself?
It is allowed to, but paths are allowed to intersect themselves. We are actually going to restrict to what are called simple paths, just to be specific, and these paths will not intersect themselves. Other people will sometimes say that a path has no intersections, and if it has an intersection, it's called a walk. But the key point is we will not consider intersections. Okay? All right, so how do we prove this? Well, we're going to use sort of an induction. Sorry, I need a little space for filling in the caveat. Induction on the number of edges with non-zero flow on them. Okay? So the base case is what? Yeah? The zero flow everywhere that was already brought up. That's the simplest of all flows, right? And that flow can be decomposed as a collection of no paths, right? So that works. So let's consider some flow. Okay. So for the inductive step, right? So the flow is non-zero, which means that there is so there's going to be a net flow out of the source. Okay? That's the sort of definition of the non-zero flow. Okay? Let's follow it. Okay? So we have the source, and there's going to be some edge carrying some flow out of the source. Okay? So if we follow that edge, we arrive at another vertex. What do we know about that other vertex? Yes?
Net flow of 0 in and out.
It has to have net flow of 0, and there is flow coming in, so what does that tell us? There's flow coming out. So we can follow to another vertex, right? We can keep doing this. How long can we keep doing this? Follow to a next vertex. That vertex has flow in, so there's flow out. Right? So we'll follow that. We'll keep following vertex by vertex, flow out, flow out, flow out, until something interesting happens. So what interesting things could happen? Remember, we're looking for ST paths. So what might we, in what way might we get lucky? Yeah. So one possibility is we hit T. Okay, now if we hit T, that means that we found an ST path. Right? And what we can do is we can subtract the amount of flow used by the minimum edge on the path. Okay? There might be different numbers here. It doesn't matter, right? We found a path, and now we say the minimum amount of flow used on any edge is 1, which means that every edge has at least 1 unit of flow on it. So if we pull out 1 unit of flow, of a path of 1 unit of flow, it will decrease the amount of flow on all of these edges by 1, right? And you notice that this will preserve the feasibility of the flow, right? We will still obey the conservation constraints because on every vertex we've decreased the inflow and the outflow by the same amount. And also, since we've just decreased the amount of flow on every edge, we are not violating the capacity constraints. Right? So we still have a feasible flow. And notice that this zeros the capacity of an edge. Why is that good? I claim this is progress. Exactly. It decreases the number of edges with flow, right, by 1. And that's going to be good for our induction, right? OK, so that's the good case. We found a path from S to T. What else could happen? Right. We could hit a previous vertex. Right? And that means that we found a cycle. And we're just going to subtract that as we do for a path. And that turns out to be the other thing that's interesting about flows. A flow can be decomposed as a sum of paths from S to T and cycles. Okay? So now we've got the whole story, right? And you don't actually have to start at S, right? Or sorry, you start at S to kind of collect all of the flow that's leaving S. As long as there's flow leaving S, you pull out these paths, or you'll sometimes pull out a cycle, right? But you'll just keep on pulling flow out that's leaving S, getting paths and cycles. Once you're done, there won't be any flow leaving S. There might still be some edges carrying flow. Just start at a vertex that has flow going through it and do the same trick. Walk out of that vertex, right? And eventually, by conservation, you're going to have to come back to your starting point, or you're going to have to create a cycle, right? And so you just at that point, you just keep pulling out cycles. And so when you're done, you will have just paths and cycles that together add up to the flow. So this is a really nice theorem because, flows are strange and complicated, but we all understand paths pretty well. And so if we can formulate things in terms of paths, it'll help us be thinking about the problem. There's another thing that follows from our analysis here. Okay? Every time we take out a path or a cycle, we zero out the flow on an edge. So how can we strengthen the statement here? Exactly. At most m flow paths and cycles, where m is the number of edges in the graph. Okay. Good. So now that we have a structural characterization, a description of what the feasible flows look like, now let's talk about this decision question. Is there a non-zero feasible flow. Here's a graph. Tell me if you can find a non-zero ST flow on this graph. How can I decide that question? Yes?
Just go searching until you ignore any zero capacity edges, and until you find T. You start with from S, and you find
Good.
T.
So what you're proposing is ignore the zero capacity. So I'm going to treat a zero capacity edge as an edge that's not there. Okay, just to remove that ambiguity. So you've got this graph with its non-zero capacity edges, and you're proposing, let's search for a path from S to T. You know, BFS, DFS, your favorite FS, right? If you find one, what does that tell you?
It tells us we have a feasible path, which is a flow.
So, if there exists a non-zero path, that implies that we can put flow on it. And so we get a non-zero feasible flow. Okay. What if there is no such path? Hold on, let me see what people, let me give people a chance to think. Yeah?
Then there does not exist a feasible non-zero flow.
So the claim is that if there is no path, then there is no non-zero feasible flow. What's the proof? Yeah, we just pointed at what we just did, right? So we already know that if there exists a feasible flow, you can decompose it into flow paths. Okay? And so if there is no path, that tells us that there is no non-zero feasible flow. So it's an if and only if. Right? There is a non-zero feasible flow if and only if there is a path of positive capacity edges from S to T. Okay? Now just to finish, if there is really no path, what does that mean? It means that if we try and do our breadth first search or our depth first search from S, right, we're going to explore part of the graph, but we're not going to reach T. Okay? So we'll start at S, we'll go out, we'll find all sorts of vertices, right? But something is going to stop us from reaching T, right? T is somewhere else in the graph, right? And it also is maybe part of a network of other vertices and edges. But there's no path that gets from the S side to the T side, okay? And it turns out that that implies that there exists a cut of the vertices of G into a set S that contains the source and a set T that contains the sink that together form the full vertex set, such that there is no edge from S to T, from the S side to the T side of the cut. People see how to prove this? Yes.
If we do our search from S, we'll hit some subset of vertices and let that be your first set.
Exactly. You just define capital S to be equal to the set of vertices reachable from the source. Right? And by definition, right, this set cannot include T, because if it did, then you would have a path from S to T, and you would have a feasible flow and so forth. So there's a set of edges reachable from the source, which does not include T, and there can't be any edges leaving that set S, right? If there were edges leaving the set S, then their other endpoint would also be in the set S. So this sets up this very interesting and important duality between paths that reach from S to T and cuts that separate S from T, right? The duality is that you have exactly one of them. Either you have a path from S to T, or you have a cut that separates S from T. Okay? Exactly one of those two things happens. And that turns out to be right at the center of thinking about max flow problems, is thinking about the relationships between paths, and flows are a generalization of paths, and the cuts that block those paths. And so that is what we will spend Monday's lecture on. So any final questions? All right, then enjoy your weekend.